So good morning, everyone. As you can see from the title, from this slide, the title is Basic and State-of-the-Art of Quantum Chemistry Method. It is indeed a very big topic, and this method can be introduced from very divergent perspective. So in my only 1 hour talk, I would like to introduce them from a native quantum chemistry viewpoint. And I hope that after my talk, you have a very basic understanding what are quantum chemistry methods and how do they perform. In computational material science, we want to know the electronic structure information of materials. This is very crucial to have a better understanding of the properties and a better design of the specific purpose devices, right? In principle, we can answer this question by solving the many electron shedding equation. This is the key message you have got from many talk in previous talk in this workshop. However, it is a very hard task because solving this equation is a 3-dimensional problem, so we need to find a good approximation. It is also another very key concept you learn from this workshop. There are several independent pathways to approach the exact solution, and density functional theory is the leading first principle method at the present because there are a number of widely used exchange correlation functions in the market with reasonable accuracy and very high efficiency. However, again, you learn from the previous talk that there are several drawbacks related to the DFT development, including weak interaction, reaction barrier high, charge transfer driven properties, and even strong correlation. These properties cannot be answered very well by current DFT. And more importantly, despite we know that exact density functional has been somewhere, but we don't know how to approach it, right? Quantum chemistry methods are rooted in the wave function theory. Unlike DFT, it provides a systematic way to approach the exact solution. Many molecular perturbation approach and couple cluster approach are two widely used strategies in quantum chemistry method to develop good approximation. Unlike DFT, wave function-based methods go beyond the mean field approximation directly and take the electron into account explicitly in the wave function expansion. Therefore, improvable accuracy together with potentially richer information make quantum chemistry method very promising for some critical case in computational material science. For example, stronger correlation-driven transition metal oxide, something like that. As you might know, MP2 and CCSDT are two most widely used quantum chemistry methods at the present. They are the name of two methods called the second-order molecular perturbation theory and couple cluster approach with single, double, and perturbative triple excitation. MP2 is the simplest wave function-based method, and its computational cost scaled as fifth order with respect to the system size. It has been 1 order magnitude higher than widely used hybrid functional, for example, PBE0, B3Lib, or HSE. CCSDT is considered as a gold standard in quantum chemistry. It can be very accurate. However, its computational cost is 2 orders of magnitude higher than the MP2 method. Before we proceed to the basic concept of these two methods, I think you would like to know why MP2 and CCSDT are the most popular wave function-based quantum chemistry method. In this slide, I would like to answer this question by their performance in several chemical interactions. You can see that CCSDT, right, is indeed the gold standard. It shows an overwhelming performance over all the other methods. And indeed, it has been used to serve an ultimate benchmark of the development of other methods in quantum chemistry. However, this method is very expensive. So most of the state-of-the-art development based on CCSDT are devoted to enhance its applicability, including large-scale parallel CCSDT implementation, aiming to have efficient use of today's and tomorrow's supercomputer. Reduce scaling CCSDT algorithm try to reduce the computational complexity without losing of accuracy. And the other kind of improvement, like couple cluster a couple electron pair approximation share a similar motivation but following a slightly different methodology. Due to the rapid growth of the computational capacity, it's now getting more and more attention of using quantum chemistry method in computational material science. We are also expecting that CCSDT can provide ultimate benchmark for solid in computational material science. Unlike CCSDT, MP2 itself is not accurate enough. However, we can see that at least it surpasses DFT in many important properties, including wake interaction and charge transfer driven properties, which are not shown here. Large-scale parallel MP2 implementation and the reduced scaling MP2 algorithm are two active topics in the MP2 implementation. And some other people try to improve the accuracy of MP2, but still keep the efficiency, do not increase the computational cost. A celebrated family of this kind of MP2-based improvement is the so-called double hybrid density function approximations. Before I briefly review, from here, I would like to review you some basic concept of MP2 and CCSDT. As I said, we can introduce that from very diverse perspective. So here I use some native quantum chemistry viewpoint, saying using elementary configuration space concept to describe MP2 and CCSDT using the so-called configuration interaction concept. Unlike DFT, most of the quantum chemistry method, to be more precisely, single reference quantum chemistry method are based on Hutchins-Fock approximation. Hutchins-Fock theory is a mean field approximation. The approximated wave function is a single Slater determinant, comprising of a set of single particle Hutchins-Fock orbital. These orbitals are determined by minimizing the energy, resulting in the Hutchins-Fock single particle equation with the well-known Hutchins-Fock operator. As I said, Hutchins-Fock theory is a mean field approximation. Therefore, it completely misses the subtle instantaneous electron-electron interactions in the model. So it has led to the most accepted definition of correlation energy made by Lufting that the so-called correlation energy is the difference between the exact energy and Hutchins-Fock energy. So take the missing subtle electron-electron into account in the correlation energy. With this definition, it is a very nature choice to develop quantum chemistry-based correlation method on top of Hutchins-Fock approximations. It leads to a very key concept in quantum chemistry method development called configuration space, which is comprised by the Hutchins-Fock ground state together of all Hutchins-Fock excited state. You see here, if we excite one occupied orbital to virtual orbital, it's called single excitation configuration. We can do this excitation so forth like that. Without proof, I just want to highlight a fact that the configuration space is complete Hilbert space in complete Basel limit, which can be used to exactly expand the wave function of any many-body shading Hamiltonian like this. It is the so-called CI expanded wave function. In the talk, for simplicity, I will ignore the electron indistinguishability. In the talk, it means that I ignore the prefactor in this expansion cluster. It does not change any conclusion I will talk and make in this talk. From this expansion, it is easy to find that we have made an actual constraint that the so-called intermediate normalization, which means the integral between Hutchins-Fock ground state and the wave function, CI type wave function equal to 0. In consequence, the integral of the CI expanded wave function is not normalized anymore. And these integrals is linearly proportionally to the number of electrons. With this definition, we can easily rewrite Schrödinger equation to the Schrödinger-like equation for correlation energy only, that is. And we can write down the correlation energy in this way. We know that electronic Hamiltonian contains only one electron operator, or at the most 2 electron operator. So, which means the correlation energy only depends on the single excitation and double excitation, because higher order excitation contains more than 2 orbitals, differ from the Hutchins-Fock ground state, right? They do not make any explicit contribution to the correlation energy evaluation. And we can write down the correlation energy in a Hutchins-Fock orbital representation like this. Because this orbital are Hutchins-Fock orbital, so they are eigenvector of this Fock operator. Therefore, the matrix elements of the Hamiltonian with single excited configuration are 0. This is the famous Brilliant series in quantum chemistry. With this theory, we can reach another way, more important series in quantum chemistry, that if we would know the precise value of double excitation coefficient, we will know the exact correlation energy. Unfortunately, all configuration of excited state, excited states indirectly depends on each other, which means that in order to get precise double excitation configuration, we need to take all expansion into account, which reach the so-called full CI expansion. And the number of the excited configuration is scales exponentially with respect to the system size. So it is very difficult to solve. Therefore, the central task in quantum chemistry is to find a better approximation to the double excited coefficient. We know that in DFT, right, the central task is to find a better approximation to the exchange correlation functional. But in quantum chemistry, it can be specified as a find better approximation to the double excited coefficient. From this perspective, the second order Molar perturbation theory is nothing but a single order perturbation treatment of the double excited coefficient. With this definition, we can expand MP2 wave function in CI expansion type and write down MP2 correlation in the famous Summer-Stay formula. However, a natural way to determine the coefficient is by solving a set of a secular equation, which is equivalent to solve a Schrödinger equation by variational principles. And the simplest CI expansion is the so-called truncated configuration integration with only double excitation, CID. And we can write down the CID secular equation in this way simply. And with this definition, we can go to the CID coefficient like this and also CID correlation like this. From this formula, we know that we should solve the CID correlation energy iteratively because it depends on the self, right? Before we proceed to more sophisticated quantum chemistry method, I have introduced you another key concept in quantum chemistry method development called size extensivity, which is saying that for a supersystem consisting of non-interacting subsystem A and B, a method which is size extensive should provide the energy of a supersystem as the sum of the energy of A and energy of B taken by themselves. It is a very crucial criterion. A method which is not size extensive has no hope to predict correct relative energy of molecules with different quality, different size. This is a key quantity to simulate, to make computation simulation in chemistry. Butler suggests that the size extensivity can be defined in a more mathematical way, which is saying that the correlation energy should be asymptotically proportional to the number of the electron m, like this. Because in condensed matter systems, which contains infinite number of electrons, so an approximation that is not size extensive doesn't work anyway. Unfortunately, all truncated DFT, truncated CID method or CI approaches are not size extensive. The typical example to make this demonstration is the cluster of hydrogen dimer molecules in the minimal base set. In minimal base set, there's only 2 orbitals, binding orbital and anti-binding orbital for H2 molecule. And we can write down Hamiltonian very easily in configuration space like this. And therefore, we can solve the CID total energy analytically in this way. And without proof, I can also show you that the analytical CID correlation for clusters with n non-interacting hydrogen dimer molecules can be written in this way. Clearly, CID energy is not proportional to a number of the systems, the electrons in the systems, right? Which means that because this behavior is lower than linear, which means in the condensed matter systems, the CID correlation is 0, which is identical to Hutchins-Fock approximation. Therefore, it is not good. But why CID or truncated CI measure is not size extensive? In 1940s, Popper tried to understand the correlation contribution in CID equation using the many-body perturbation strategy. He suggests that if we start from MP2 correlation and MP2 wave function in the CID equation iteration, after first iteration, the CID correlation is MP2 energy plus third order correlation correction. And higher order many-body correlation will be introduced during the iteration and iteration. It is one kind of renormalization of many-body perturbation theory. However, CID equation contains the second type of the renormalization. You see, the lower level energy will be renormalized in a certain amount, right? Without proof, and I will show you later, monopolar perturbation energy are size extensive, is proportional to a number of electrons. And as I show you above, any CI type expansion, the integrals of themselves are proportional to the number of electrons, which means that the correlation energy, CID correlation energy, has been not size extensive even after 1 iterations, because the lower level correlation, many-body perturbation energy will be rescaled or renormalized. To have a deeper understanding, I show you the MP2 correlation in diagrammatic representation like this. We know that MP2 correlation contains 2 linked second-order excited diagrams. This is direct term, and this is exchange term. And in CID equations, these 2 terms will be renormalized by a factor. And you can easily find the duration from any typical textbook that this renormalization term can be rewrite into several unlinked fourth-order excited terms, but with a negative prefactor. But what is linked and unlinked correlation means? For simplicity, I will consider them as 2 different correlation modes in many-body correlation. The so-called linked correlation is the correlating mode, which involves and entangle all electrons in the interaction. And unlinked correlation contains several independent sub-correlation modes, which are linked by themselves. Without proof, I tell you the fact that the linked correlation are size extensive, but unlinked correlation are not. Okay? Keep this figure in mind. I can show you a very important observation from this derivation that the renormalized diagrams in the truncated CI expansion are not size extensive. However, this term can be exactly eliminated by the unlinked high order excited diagrams. With this observation, I can guide you to some important conclusion in quantum chemistry method development. In many-body perturbation point of view, because linked diagrams are size extensive, but unlinked ones are not. Therefore, we cannot include unlinked diagrams in correlation in the many-body perturbation expansion. Luckily, the monopolar perturbation theory satisfies this constraint. It is also why we call monopolar perturbation theory as linked theory, diagram theory. In other words, MPN method, including MP2, are size extensive. However, in configuration interaction approach, they renormalize the linked diagrams. Meanwhile, include unlinked diagram. Both of them are not size extensive. In full CI, which is the exact solution of a Schrödinger equation, which the renormalized low-order diagrams cancel out exactly with some unlinked diagrams in higher order. Therefore, it is size extensive. Unfortunately, this cancellation breaks down in the truncated CI method because, to be specific, CID is not size extensive because it contains renormalized second-order diagrams. However, the unlinked fourth-order diagrams are completely excluded. So how can we go further to make the CI expansion type wave function size extensive? We know that we can, to understand this question, we can consider electron correlation cluster by cluster. The so-called truncated CI is trying to distinguish electron correlation by the number of electrons. So the CID correlation, equation contains two electron correlation clusters like this, right? The CISD is to take another correlation cluster called one electron correlation cluster into account. However, truncated CID method cannot distinguish linked and unlinked clusters, which are key concepts to address the self-intuition problems in the size extensive problems in quantum chemistry method. To be specific, I list the connection between the linked and unlinked cluster up to the fourth excitation. On the right-hand side, on the left-hand side, it is the coefficient of the CI expansion, and they can decouple to linked diagrams and unlinked diagrams. The blue one are linked diagrams, which are renormalized partially in the CI iteration, and the red one are unlinked cluster at the fourth order and third order level. They are very crucial. They are very important to cancel out the renormalized term in the lower level, but excluded in the CISD approximation. Therefore, the so-called couple cluster approach is the most elegant way and most efficient way to take unlinked diagram in high order into account with the same excitation level. Okay? Therefore, the full cis-couple cluster approach is identical to the full CI method. In principle, they are exact. Meanwhile, the couple cluster approach approximation with the same excitation level share the same computational cost as the CI approach with the same excitation level. For example, cis-SDT share the same computational cost to CISD. More importantly, cis approach are size extensive. Recently, it has become possible for small molecule to pursue very accurate description of in cis-SDT and cis-SDTQ. However, the computational costs are very, very expensive. On the other hand, we realize that we should go beyond cis-SD if high accuracy is required. One of most successful compromise is the so-called gold standard cis-SDT model, which take the three perturbative correction to the converged double excited coefficient of cis-SDT calculation. The triple excitation correction features and seventh order scaling with respect to the system size and read like this. This figure I show you the arrow in CI and cis approach in the total energy calculation of CO molecules. And you can see that with a given excitation level, CC model are about one order of magnitude more accurate than the CI model. And this observation will become even more significant for larger systems. And in extended systems, CC approach hold the possibility to be accurate. But CI doesn't work because they are not size extensive. To summarize, in this section, I try to introduce MP2 and cis-SDT method in a native quantum chemistry viewpoint, in particular in the expansion of the so-called configuration space with the CI types expansion. Due to the intermediary normalization constraint in this expansion, we can write down the correlation energy, which depends on the double excitation configurations only. And size extensivity is a very important property in the quantum chemistry method development. And both MP2 and CSSDT are size extensive. It is the theoretical guarantee of using this method to large and even extended systems. We know that density function theory is the working horse in computational material science at the present, and the quantum chemistry methods are not so productive, right? Because they are too expensive. However, endless and active are the development toward higher accuracy and higher efficiency based on MP2 and CSSDT. Here I will show you some challenge and state-of-the-art developments of these two methods. Unlike CSSDT, MP2 itself is not accurate, so we need to make improvement on top of MP2. At the present, there are two different ways to go. The first way is somewhat not empirical. This is the diagrammatic representation of MP2 I showed you above, direct term and exchange term. The widely used fifth order density functional method in DFT is the so-called random phase approximation, which can be considered as a renormalization of the direct term by including higher and higher order bubble ring diagrams into account. However, random phase approximation RPA itself is suffering very heavy self-correlation error. It means that for one electron systems, RPA provide non-zero correlation energy. It is very crucial, okay? So we need to do a similar renormalization of a second order exchange term, which is called a source-sect correction to the RPA. And Singh realized that if we put many-body perturbation theory in DFT context, it means that we now expand the configuration space using constant orbital but not touching Fock orbital. Then the Nussbaum theory I show you above doesn't hold. So the single excitation indeed explicitly contribute to the correlation energy. If we make the renormalization of this term as well and take three renormalization terms together, we reach the so-called renormalized second order perturbation theory, RPT2. Singh demonstrated that compared to RPA and standard MP2 method, RPT2 can show a significant improvement in the description of several chemical interactions. However, the price, of course, is quite a high actual computational effort. Another way to go is somewhat empirical, which try to improve the accuracy of MP2 method, but without losing the efficiency. A successful family of this kind of MP2-based improvement is the double hybrid functional. The double hybrid here means that we try to introduce Hutchins-Fock-like exchange and MP2-like correlation in the functional formulation. And if we take this formulation and optimize the parameter with respect to a set of thermochemistry data, I can introduce my first hybrid function called XRG3. I show you that XRG3 can be extremely accurate for at least main group element. So for reaction barrier height and weak interaction, XRG3 results are in a very good, excellent agreement with the result provided by CSSDT, which is the benchmark data for almost all the functional developments in quantum chemistry. Slow basis set convergence is a very big challenge for the use of quantum chemistry method, because in this quantum chemistry method, we try to expand the wave function in CI configuration space. Okay, so we try to explicitly take electron into account in the function expansion. It results in the so-called electron pair wave function, which behavior features a cusp condition when two electrons get close to each other. Unfortunately, none of the existing basis set can describe this cusp condition effectively. So the most popular way to converge MP2 and CSSDT result is by using the so-called basis set extrapolation scheme for this kind of formulation, more or less. In order to have a good and accurate basis set convergence extrapolation, we indeed need a sequence of basis set which can show a consistent convergence of correlation. Based on this convergence behavior, we can make an extrapolation. Otherwise, it doesn't work, right? And in FHIMs, you know we are using numerical L10 center NAO-based set. We also provide you a series of NAO-based set with valence correlation consistency called NAO-VCC-NZ, which is now the default choice in M's code for advanced correlation method, including MP2, CSDT, RP, and so forth. Another way to address the base set issue is the so-called explicit correlated method R12, F12, which is trying to introduce the electron-electron distance in the CI expansion, which means that we introduce orthogonal complement to the Hutchins-Fock configuration space. Due to the different way to generalize this orthogonal complement of a configuration space and a different way to generalize an actual four-center integral needed in this method, there are many variants of R1 to F1 are proposed in quantum chemistry. If you are interested, you can take a look of this very nice reviews paper in Chemical Review. But anyway, high computational cost is the main barrier for a practical and routine use of quantum chemistry method. From this figure, we can see that compared to PPE and PP0, the computational cost and memory consumption of MP2, the green one, right, and the red one for CSDT increased dramatically and very, very quickly. To address this challenge, people try to use the resolution of identity to reduce the memory consumption of CSDT and MP2, which is a technique to decompose the fourth rank electronic repassive integral to several third rank quantities like this. And resolution of identity has been used to combine with MP2 and CSDT in many different perspectives. And we can further improve the memory performance by decomposed first order quantity to second order quantity even by utilizing the locality in resolution identity. This is the work in our group and has been published 2 years ago. And the so-called tensor hypercontraction scheme is another kind of more mathematical way to decompose higher order tensor to low order. Some people have shown that tensor hypercontraction scheme is very promising for MP2 and CSDT implementation. However, accuracy and numerical, and particularly numerical stability, need validation and investigation systematically. For computational timing, you see, CSDT is infeasible, right? The calculation of CSDT is infeasible for any real systems. This is the plot for very simple hydrogen water clusters with double theta base set. You see that with 30 waters, we need more than 2 months for CSDT calculation. On the one hand, we can address this challenge by utilizing use the full power of today's supercomputer. It means that we need higher or large-scale parallel implementation with high parallel efficiency. You can imagine if we use if we have an implementation with perfect parallel efficiency, we can reduce this calculation to 1 day if we take 100 courses, right? On the other hand, we can try to reduce the computational cost by reduce the scaling from 7th order to lower order. This is the so-called reduced scaling algorithm. This kind of concept try to use the near-sizeness of correlation in physics. However, this concept cannot be used straightforward because canonical MP2 method and canonical CSDT are represented in a molecular orbital by using molecular orbital, which are delocalized. So we cannot straightforward utilize locality in correlations. Two popular ways to solve is take advantage of some sophisticated mathematical transformation and rewrite MP2 or CSDT formulation into the representation based on atom center orbital base set or localized molecular orbital. If you are interested in this topic, you can start reading from some reference I show you here. Okay. Recently, it is becoming more and more interest to implement and test quantum chemistry method for periodic case. However, in periodic boundary condition, the challenge I mentioned above becomes more serious. Unfortunately, most of the state-of-the-art development I mentioned above were proposed and manually validate in finite molecules. Okay? So here I briefly show you some current progress in our FHIM's code. To be specific, we now have canonical MP2 and canonical CSSD for both molecules and solid. The complete CSSD-T is now available for molecules, and the periodic version is coming soon. More importantly, we now have a reduced scaling MP2 implementation to large molecule and large solid with hundreds of atoms. All these implementations are using the resolution of identity and featuring a high parallel efficiency. This is a flowchart of periodic MP2 implementation in M's code. The parallelization is designed with respect to both K-grid and molecular orbitals in order to achieve high efficient distributed memory calculation. We use the scalar pack blocks to distribute 4 center integers and the corresponding 3 center I coefficient. We have demonstrated that very high parallel efficiency can be achieved in commutative supercomputers up to several thousands of CPU. Here I selected show you the basic convergence of our periodic MP2 result for several several crystals with cubic structure, diamond, silicon, MgO, and ALP. From this figure, we can see that the base set is not a big issue to converge for lattice constant or Bach modules, like geometry, the so-called geometry information, right? The third order, the NAO triple theta base set has been good enough to approach the desired accuracy if we compare to the complete base set limit result. However, the slow base set convergence is indeed a big challenge, a problem for the cohesive energy calculation. Compared to the complete base set limit, the base set error in the 4Z base set are still remaining about 100 millieV, you see, for all different kind of materials. One of big challenge in real and daily chemistry is that we need to find a good approximation which can describe both molecules and solid in a balanced way, right? It's extremely crucial for the catalytic systems because the catalysis procedure is in principle related to the bond breaking and forming of small molecules. However, accommodation of the Bach is essential to the catalysis effect. B3 functional is very popular in quantum chemistry because it can provide quite accurate description for molecules. Here I take G2 with several hundreds of molecules into account. The mean absolute deviation is only about 130 millieV. However, it doesn't work or works very bad for solid. Here I take 10 cohesive energy. For example, you see the mean absolute deviation is about 400 millieV. For comparison, the PBE type of function performs much better for solid, but for periodic, but it's not satisfied for molecule. MP2 method itself is not accurate, but here I show you that the MP2 based improvement, the double hyperfunctional, can indeed provide a very good balance to describe both solid and molecules. Our reduced scaling MP2 implementation is using Laplace transformation, okay, to rewrite MP2 correlation into atomic orbital representation. However, unlike standard formulation, Laplace transform MP2 need to take another kind of 4 center integral into account, the so-called the contracted 4 center integrals. Compared to the standard for center integral. This kind of quantity is a little bit more delocalized, despite still localized. So we develop an adapted localized resolution of identity to reduce the computational cost in our Laplace transform MP2 implementation. We first examined our mass development using a cluster with 10 waters to 150 waters. The black curve is the practical total energy of canonical MP2 calculations. We see that the scaling, the computation scaling is fourth order with respect to the system size. It is dominated by the generation of Ri coefficient, the standard Ri coefficient. For comparison, our Laplace transform MP2 implementation, the yellow one, right, features a near quadratic scaling with respect to the system size. More importantly, the break-even point happens way earlier, belong to cluster 20 water cluster and 30 water clusters. I would like to emphasize that this very good efficiency, performance can be achieved without losing any accuracy because very high screening criterion has been used to suppress the MP2 correlation energy error below 1 millieV for the whole plot. Our Laplace transform MP2 is also available for periodic case. Here I show you the performance for for water molecule absorption on the titanium oxide surfaces. This is the plot for the numerical convergence of water absorption energy with respect to the model size in different direction, layers, the layers and X and Y, Z direction. In order to achieve 20 millieV accuracy, we need to use at least 3 layers together with 3 by 4 surface layers, which contains more than 200 atoms. Apparently, canonical MP2 cannot handle this kind of systems efficiently and practically, which highlights again the importance and the timeliness to develop lower scaling quantum chemistry method for solid. Our CCSDT implementation is using resolution of identity technique. As I show you, the resolution of identity CCSDT implementation has been proposed several years ago. However, there's no systematic accuracy validation of this kind of approximation because there's no RI method, there's no RI base set specifically optimized with respect to CCSDT energy. And in our project, we're happy to see that the RI base set we use in FHMs is very good, and which can be used to converge CCSDT result within 1 millieV compared to the canonical and analytic CCSDT implementation with the same base set. And in maximum, the error is lower than 3 millieV in total. And we also use 1 dimension, 2 dimension, and 3 dimension systems to demonstrate our implementation. We see that the parallelization efficiency is quite high and can be scalable to thousands of CPU. Here we use around 2,600 cores, and a very high efficiency can be achieved with thousands of CPU. We also test the numerical convergence of our CCSDT implementation in finite cluster model and periodic boundary model with respect to the cluster size and unit cell size. And we can see that it can converge to the same result. In the complete actuability limit, the discrepancy can be lower than 2 millieV, which indicates our CCSDT implementation can handle both molecule and solid in the same numerical footing, which is very crucial if you want to use the method in your real application, and you also want to compare if the cluster model or its periodic model is a better choice for your specific research. So in summary, I show you some basic knowledge of quantum chemistry method and also briefly review the challenge and state-of-the-art development of this method. Later on, I show you some relevant progress in our FHIM's code. Considering that the computational power increased very very quickly. So we cannot imagine how powerful of the computers in 10 years later, right? And also considering that we have quantum chemistry method can provide quite critical power to some very crucial cases in computational material science. For example, strong correlation related to transition metal oxide or some other charge transfer driven properties. I think quantum chemistry method will definitely attract more and more attention in computational science. So it is a time for you to get some knowledge. What is quantum chemistry and how do they perform? It is the target of my talk, and I hope I make it. And in the end, I would like to thank Matthias for his last support in my group, and also acknowledge two people who are key persons in a very challenging project in this talk. In the end, I would like to thank you for your attention.